Hey everybody. So slope fields, kind of cool, kind of labor intensive. Um, I'd like to start talking about what our next method of what our next method of integration will be. Um, and that is, and it's sort of in a list. Like if I recognize the derivative and know it's antiderivative, I do that. Um, if I if I see a differential equation, I can do separation of variables in many cases and solve for an antiderivative that way. Well, now what I want is when I see a function and its own, or at least part of its own derivative. When I see a function and its own derivative present, this is a signal to use u sub. Okay, so we're going to be looking at u subs today. I will tell you that in general, the challenging part for a lot of people with u subs is figuring out what the u is, and often we start our u sub experiences with things that many of you do in your head. But I'm going to say, the people who do them in their head, it just makes it harder for them to actually then use the u sub when they really need to use the u sub. So I'm going to encourage you to use the u sub when you see things. So, for example, if I see the integral of cosine of 4x dx, I'm going to make u equal to 4x. Now, what's causing me to say that? Well, that function is inside of this one. And often my u is less accessible. It's inside another function, it's in a denominator inside a function. It's harder to get at, is a way I might describe it. So this 4x is definitely inside this other function. So what I'd like to do is say, all right, I might be able to find the antiderivative here, but if I rewrote this, not in terms of x's like it is now, with this x and this dx, but if instead I rewrote things in terms of u, then, maybe I could have an easier time with this integral. Well, no problem here, because I know that 4x is equal to u, and so this is just cosine of u. Now, what about dx? Well, dx is something that I can get by taking the derivative of this expression. Okay? So if I have u equals 4x, and I take the derivative of u with respect to x, I know that derivative is going to be 4. In fact, because I know about differentials now, I can say that du is going to be 4 dx. Well, I see a dx, but I don't see an extra 4 floating around. If I divide both sides by 4, then I know that dx equals either du over 4, or you could write 1/4 du. So this came from, okay, I'm replacing 4x with u. But now I have to replace dx. dx is equal to du over 4. Or if you like, you can bring that 1/4 over here, and since it's a constant, you could even bring the 1/4 all the way out. Okay, so while I might not have been sure how to handle that thing in there, that 4x in there going backwards, now I don't have to worry about that. I just have to do the antiderivative of cosine. which is sine of u plus c. Remember, though, the antiderivative of cosine has this 1/4 in front of it. So there's this 1/4. And then finally, we want everything in terms of x. So even though we started with x and moved to u, we want to go back from u to x using that u sub. And so there's my answer. Now, again, if you're not sure, the way to get sure about this as your answer is take the derivative. The derivative of the constant is 0. Great. The derivative of sine of 4x is going to be cosine of 4x times, because chain rule, derivative of the inside function would be 4. But I don't see a 4 there. There must be something on the original function so that when I take the derivative and that 4 shows up, it gets canceled out. And lo and behold, there's no 4 or 1/4 here. They get canceled out. So when am I doing u sub? Well, one way I can think about a u sub is I see a function and its own derivative, but I also know now that a u sub is used to light. A u sub is used to undo chain rule. That's what I'm doing with my u sub. I'm undoing chain rule. And the indication that I want to use the u sub is I see a function and all or part of its derivative. Okay, so if I see something like 6x cosine 3x squared dx, if I have to integrate this, well, I see a function. Ooh, I see a function and I see its derivative. Whenever I see a function and its derivative, or even if I saw part of its derivative, I would say u sub. And whatever that function is whose derivative I see, that function turns out to be my u. U equals 3x squared. If I take the derivative of both sides with respect to x, I get du dx equals 6x. Or du equals 6x dx. So now look, I've got a 6x and a dx. 6x dx is replaced by du. And 3x squared is u. And so my integral becomes cosine u, and then 6x dx is du. Well, there it is. And so what's the antiderivative for this? Well, I know the antiderivative of cosine of u will be sine u plus a constant. And what's our u? This is our u. Remember, you should always sub that x stuff back in when you're done with your u sub. You can always, of course, take the derivative of your answer. It should be this stuff here. The derivative of sine is cosine, leave the inside alone, times the derivative of that inside, 6x. Ta-da! So a u sub can help me undo a chain rule. A u sub can help me integrate stuff that I don't necessarily recognize. So if I see 3x plus 2, what am I going to do here? Well, I'm going to say, hey, I don't recognize that derivative, but I do recognize this is the derivative for ln of x. So what if I make this my u? U equals 3x plus 2. du dx is 3, or du is 3 dx, or even dx is du over 3. So I want to get rid of the dx, and I want to get rid of all this x stuff. So I can turn this stuff into 1 over u, and dx is du over 3. I'm going to pull 1/3 out, 1 over u du. It's my job to recognize this as ln of u, and if you don't recognize this as ln of u, you need to go back to the last video and go through the practice of all those. You should probably go back to chapters 3 and 4 and review your derivatives. Make some flashcards and get to work on that, because you have to recognize that this is the derivative of ln of u. We have a 1/3 stuck on with multiplication. Don't forget the plus c. Now, can we stop here? No. Back substitute. So we're going to have 1/3 ln 3x plus 2 plus c. So there's my u sub. All right, well, I think it's your turn now. So how about the integral of x plus 2 to the 5th dx? Please use u sub here. Go away, try it, come back when you have a question. Okay, hey, welcome back. Was that fast? Are you not sure what your u is? Yeah, that's my u. Remember, u is the inside thing. U is hidden in the denominator thing. U is less accessible. And so that's our u. U is x plus 5. I know. You said, Mr. Kukla, that I should see a function like x plus 2 and its derivative. And you know what? I do. See that 1 over there? That's going to be the derivative of that. So yeah, I do see a function and its derivative. Okay, so why don't you pause again and actually go give this a try. So, welcome back. Did you determine that du dx was equal to 1? And so du equal dx? Because we're going to need that when we want to get rid of this dx. We can replace with du. And we're going to replace x plus 2 with u. So this integral becomes u to the 5th du. Well, how do I find the antiderivative of that? That's going to be u to the 6th over 6 plus c. And don't forget, we don't want our answer in terms of u. We want our answer in terms of x. Okay, there's our antiderivative. All right, well, so we're starting with some nice gentle ones. How about you do this one? The integral of square root of 4x minus 1 dx. Okay. Can you determine the u here? What would the u be? If you said 4x minus 1, because that's the inside function, I think you're moving in the right direction. So let's say that u is 4x minus 1, and we take the derivative of both sides, and we get that. And I know I don't see a 4 here. There's no extra 4 floating around. But that's okay, because what I do see here is a dx. I need that dx. In fact, I don't really want the 4 and the dx on the same side. I want to know what dx is. So I can rewrite this integral as square root of u du over 4. And I could, take that further by pulling out that constant 1/4 and rewriting this as u to the 1/2. So what's the antiderivative of u to the 1/2? Well, isn't that going to be add 1 there, so I have 3/2? And I don't see a 3/2 down in front, so I'm going to need a 3/2 here, which is the same as having a 2/3. Now that 1/4 is still there, and so we might want to tidy this up to be 1/6 u to the 3/2 plus c. Okay? And don't forget to plug back in what we had for u. So that's going to be 1/6 4x minus 1 to the 3/2 plus c. And how do we check this? Well, we check it by taking the derivative. I would take the derivative of the outside and bring down that 3/2. And look what happens. 3's cancel. I got 2 times 2 for 1/4. Ooh, that's good. And the derivative of the inside function is going to be 4, and so that 1/4 times that 4, they cancel. And so all I'm left with then is 4x minus 1 to the 1/2 power. And so I do get back to my original. Trying to do this, trying to come up with this in your head is really, really hard for a lot of people. And so I think U sub is definitely the way to go. We're going to be doing U subs the rest of the year in this class. So I would recommend embracing U sub rather than shying away from it. Okay, so what if I have this? 2x square root 1 plus x squared dx. Do you see a function and its own derivative or part of its own derivative? Why, yes, I do. And some people say u and there's its derivative, but take as much as you can for your u. That's going to be my u. My u is 1 plus x squared. Could you do it with u equals just x squared? The answer is yes, but in this situation, some students would want to do another or a double u substitution. And so I'll walk through that one in a minute, but let's just do this one because I think you should be comfortable, or at least in the doable place, with this u. So using this u, please do a u sub, evaluate, find the antiderivative, and back substitute this in when you're done. And then we'll talk about doing the problem with this u, all right? Okay, hey, welcome back. I hope it went well. Did you come up with du dx equals 2x? And then, in fact, I would multiply both sides by dx and get du is 2x dx. Now, you could divide both sides by 2x, but I notice here that I have a 2x dx. And so I'm going to replace all of that stuff just with my du. Okay? And this here gets replaced with u. So I have square root of u du. Whoa, that's so much less complicated. I do want to think about u to the 1/2 power here so that I can add 1 and divide by 3/2 or multiply by the reciprocal 2/3. So I'm going to have 2/3 u to the 3/2 plus c. And don't forget to plug this back in. So really, I want 2/3 1 plus x squared to the 3/2 power plus c. Okay? There's my antiderivative using a u sub. I did the u sub of all that stuff that was inside the square root function. And in fact, the derivative of all that stuff was right here. So I did that, but I know some of you wanted to use just x squared for your u. Okay, so I've got 2x square root 1 plus u dx. And in this situation, I know that du dx is equal to 2x. I see a 2x. In fact, I can multiply both sides by dx. And there I go, du is 2x dx. Oh, great. 2x dx. So I can replace this and this simply with du. du. And here I have square root of 1 plus u. Now that's fabulous, except that there are people who don't know how to do this antiderivative. Even if I rewrite it as u plus 1 to the 1/2, no. And so in fact, students who don't take as much as possible for their u, they sometimes have to do a second or a double u substitution. And so what would my w be? My w be u plus 1. And dw du would be 1. So dw equals du. So I can rewrite this u integral now with w stuffs. U plus 1, that's w. So I'm going to have w to the 1/2, and du becomes dw. Aha! There's my double u substitution. So the antiderivative here would be w to the 3/2. Ooh, don't forget that 2/3 there in front, so that when I take the derivative, this comes down, they cancel, and I just get that 1 there. But wait, we know that w is u plus 1. And so now we could write this as 2/3 u plus 1 to the 3/2 plus c. Oh, but wait a moment. Our u was x squared. And so now I have to replace this with x squared plus 1 to the 3/2 plus c. And there it is, same answer, but because I didn't know how to do this antiderivative, I had to do a second u sub, or a double u sub, as is the case here. Okay? All right, so with that being said, how about, maybe it's time for you to do a couple. All right, so here's yours. 1 over square root cotangent x times cosecant squared x dx. Please find the antiderivative. Use a u sub to find this antiderivative. Did you get the u? Are you okay with the u? I hope your u was cotangent x, so that your du, negative cosecant squared x dx, well, I'm a little troubled by this. Did I really have that problem? Oh, it's not in the denominator. My bad. I read my original problem wrong. Yeah, we would have gotten into big trouble if that denominator had actually been where we were. No fraction, it's just this. Phew. Okay, so there's my u. Here's du. I see a cosecant squared. I see a dx. I don't see a negative, though, so I'm going to divide both sides by negative. So I can replace all of cosecant squared dx with negative du. So this is going to be square root of u times negative dx. Oh, negative du. And, negative, I just don't want it to become a subtraction symbol, so I'm going to pull that out in front. I have u to the 1/2 du. And now here, what can I do? Well, I know the antiderivative of u to the 1/2 is u to the 3/2. Don't forget the 2/3 out in front, and the plus c, and that negative. And what was your original u? U was cotangent x. We've got to plug that back in. So negative 2/3 cotangent x to the 3/2 plus c. All right? All right. I kinda want to just do a whole bunch of these with you, but actually I want to look at two more issues. Maybe 3. Jeez. Okay, how about the integral of 1 over cosine squared 2x dx? What would my u be here? Well, no, it's not going to be sine. And I know you say, but I see cosine. Yeah, so here's the thing. If I make u equal sine, or even cosine, this is then u squared. So no, I don't feel comfortable with that. I do, though, remember enough trig to say, well, isn't that the same as secant squared 2x dx? Sure is. And I know that secant squared is the derivative of tangent. So, actually, that's my u. U is 2x. So with u equal to 2x, please finish up this problem and come back when you're done. Hey, welcome back. Hopefully you got to u dx is 2. and du equals 2dx. Well, I don't see a 2 out here. I see the dx. I think I'm going to divide by 2. And I can replace dx with du over 2. And I can replace 2x with u. So this becomes secant squared u times du over 2. And I can migrate that, divide by 2, out in front. Whose derivative is this? This is tangent. Tangent's derivative. Don't forget that constant out in front. Don't forget the plus c. And don't forget to replace u. So we've got 1/2 tangent 2x plus c. So, yeah, about this trickery over here. One of the reasons we study trig before calculus is so that we know our trig identities and can use them. I don't recognize this derivative. I should really recognize that derivative. Okay. And often we need to do some manipulation before we even do our u sub. For example, in this situation, thank you, wife. I have no way to stop recording this video, so I'll be with you in a bit. Okay. All right. When I think about this, I pull out that 42. I have 1 over x squared plus 36 dx. And you know, it kind of looks like the derivative of inverse tangent. But this would need to be a 1. So, let's turn it into a 1. We're Americans. We make things be the way we want them to be. But you know, I can't just randomly divide stuff by 36 unless, like, you know, I divide here by 36 as well. In fact, I can't even do that just because I'm an American. In fact, I would need to simultaneously divide by 36 and multiply in the denominator by 36, right? Because then those 36s would cancel. But no, I don't want to cancel them, right? Because I wanted this to become 1. This is x squared over 36, which is a little uncomfortable. And then here on top, I have 1. I got this 42 out in front, and I've got this 36 that can come out in front. So here we are. We have not done any u sub yet. We've just algebraically manipulated this so that I could have the thing squared plus 1 on the bottom that works for inverse tangent. Now, what's my u here? Well, it turns out my u is x over 6. How come? Well, let's square both sides. If I square both sides, I get u squared equals x squared over 36. X squared over 36. That's u squared. So then we're going to have, oh, by the way, I can reduce that to 7 over 6. Here I have 1 over. X squared over 36 is u squared plus 1. And did we ever get a derivative of this? Oh, no, we have not yet. So du dx is 1/6, or 6 du is dx. So I can replace the dx with 6 du. 6 du. Oh, and in fact, those constants can cancel. So 7 integral 1 over u squared plus 1 du. Now I have the inverse tangent. So 7 tangent inverse u plus c. And what was our u again? The improbable x over 6. There we go. That is our antiderivative. And remember, if you're not sure, you can always take the derivative of this thing. If I take the derivative of inverse tangent, I'm going to have 1 over stuff squared plus 1 times the derivative of the inside function. That gets me that 1/6 that we were looking at before. And so I'll be able to get back to this in short order. Less obvious. Guess what? Really common. Practice this one. I think whenever we get to sections where there are mechanical differentiation or integration techniques like learning chain rule or learning U-subs, really, you should practice them enough so that you don't have to think about them when you do them. Like, I would love it if you looked at this 2 plus sine t dt and said, oh, I know what u is. U is 2 plus sine t. All right. How'd you get that so fast? Well, it's on the bottom, and I see its derivative is up there on the top, right? Isn't the derivative of sine going to be cosine? So we've got we've got cosine t dt. Here's cosine t dt. So this is going to be 6 over u and du. Very nice. And so I can pull that 6 out, and now I've got 1 over u, and this is 6 ln of u plus c, or 6 ln 2 plus 2 plus sine t plus c. Okay? But, Mr. Kukla, what if I chose the other one? All right, well, let's see what happens. U equals 6 cosine t. So du dx, or du dt, is going to be equal to negative 6 sine t. And if I multiply both sides by dt, what I notice is the dt and the sine t are on the same level. And up here in this original problem, dt is on the top and sine t is on the bottom. Wah. So that tells me I chose wrong. I'm not going to be able to make that substitution work. So, yeah, try the bottom before you try the top. Okay, next. The last thing that I feel like we really need to take a look at is, instead of indefinite antiderivatives, these indefinite integrals we've been doing, what happens when we have bounds on our, what happens if we have a definite integral? So I've got tan x secant squared x dx, okay? So here is my integral, and I'm supposed to evaluate it. Well, I see a function and its own derivative. So u is tan x, and du dx is secant squared x, or du is secant squared x dx. Great. Secant squared x dx is du, and u is tan x. So this becomes u du. What a gentle integral. Now, if I do this, I'm now going to be losing some points. Why? Well, these are the x bounds. They're not the u bounds necessarily. Shall we go about finding some u bounds? No worries. Take these x values and plug them here in for x to find out what the u bounds will be. So if I take a 0 and say, what's the tangent of 0? Well, the tangent of 0 is 0. But if I plug a pi over 4 in here, the tangent of pi over 4 is 1. So my u bounds now are 0 to 1 instead of 0 to pi over 4. Now, you've got two choices once you've got some u bounds here. The first one is to do that antiderivative, u squared over 2 plus c, and then evaluate the antiderivative with your u bounds, 0 to 1. And so I end up with 1 squared over 2 minus 0 squared over 2, or 1 half. Okay? I evaluated this integral using the u bounds on the u. But you could also, once you did this antiderivative of u squared over 2 plus c, and did that substitution back in, so our u was equal to tangent, now we've got tangent squared x over 2, and we want to evaluate this one. Don't evaluate this one with your u bounds. You need to evaluate this one with your x bounds, 0 and pi over 4. Okay, so we're going to have 1 half. Tangent of pi over 4 is 1. 1 squared is 1. And tangent of 0 is 0, 0 squared is 0, and lo and behold, I get that same 1/2. So I can evaluate my u antiderivative with u bounds, or I can back substitute what u was equal to and evaluate with my x bounds. It's often actually easier to evaluate with your u bounds, but students feel much less comfortable with that. The whole finding those u bounds. How did we find those u bounds? Well, remember, we had this thing called u equals tangent x, and we took each of those x bounds and plugged them in there to get corresponding u values. Now, the only thing you need to watch out for is don't put x bounds on a u integral. If you do, in our case, we had originally this tangent x secant squared x dx, and this would have been fine, but because those are u bounds, but this is not gonna be fine if we plug 0 and pi over 4 here. No, that's wrong. Don't do that. You actually have a choice. When you get to that integral u du, you could put the u bounds on or no bounds. If you leave no bounds, not a problem. Come over here, u squared over 2 plus c, no bounds. But when it comes time to evaluating this, either you're going to evaluate this u antiderivative with u bounds, 0 and 1, or you're going to turn this thing back into some sort of x thing and evaluate with your original x bounds. All right, well, I hope that this was helpful, and I look forward to a couple more videos of practicing u subs and going backwards in general. Take care, everyone.